let's go ahead and get started. So one of your peers came and talked to me and said, okay, we've been discussing like a lot of really weird abstract things, and I'm just having trouble figuring out how to put it all together into one clean framework. And I said, yeah, that pretty much tracks with how Phys 2 goes. So, because that's where, I've been teaching this as my like 7th time through this class or so, or at least a class similar to it, and I recognize that I too struggled with this, and so the question is, how in the world can we bring all of this together? And so I just want to remind us, over the previous 6 days in class that we've only had 6 days in class so far, but we've covered a lot of ground. What in the world have we covered so far? What's the roadmap, and how do we link all of these different things together? And I want to ask you guys, we started on day 1 with a very simple understanding that there is this thing that exists in the universe. There's this fundamental property of matter. It's not mass, but what's the other fundamental property of matter that we discussed on day 1 that we've been talking about ever since? Electric charge. We state that there are such things as charges, and I'm going to represent that with a little guy Q there. Now, we said after that, when charges come into contact with one another, so if I bring another charge here into existence, what happens between those two charges? Coulomb was the guy who helped us wrap our minds around this. They're attracted or repulsive towards one another, and we said then that they therefore experience a force, right? Okay, and this is where you were like, okay, yeah, there are charges, they repel and attract, but everything kind of breaks down for me from there. Okay, you're with the remaining 90% of other students in this class, right? So where we took our first deep dive into something that was maybe a little bit more confusing, we said, okay, if we then divide out this other charge Q, then what's left over essentially from this first charge that existed to begin with? What's left over when we take a force and then we divide out the thing that's experiencing the force? You get an electric field, exactly. So we've got this electric field that is left over. It is essentially the map of what would be experienced if you bring in a charge into that field, right? Then you get a force. So that's where we spent the first 2 or 3 days. You have charges, you have forces, and you have fields, and this is how they relate to one another, right? So then we go into physics 2, back to physics 1, and it turns out that if you take the integral over this force, since the force is conservative, what do you get left over when you integrate F dot dl? Specifically, I guess I need a negative sign out front here for this to be true. What do you get when you integrate a force over some distance and then take the negative of it for a conservative force? Work is F dot dl, and if we take the negative of that, we said that the change in potential energy for a conservative force is equal to negative work done. So we've got U is the potential energy stored in the system, right? And we can take the reverse of that by going backwards along this by saying the derivative with respect to the position is going to be the force. right? So we can go either way along any of these paths here. And because we only care about the derivative, not about what u is, we're asking implicitly, okay, how is u changing? Or how could u change? Not u specifically, but u, the potential energy function. Right? And then we said, okay, if there is such a thing as potential energy, it turns out that we can divide the thing that's experiencing potential energy, and what's left over is a map, and we called that map what? This was just last class period. The electric potential, or voltage, whichever you prefer. Electric potential or voltage, meaning that if we take voltage and we multiply it by a charge within that voltage, it's going to give us the potential energy of the charge in that electric potential. Right? Well, it turns out that exactly the integrals and derivatives that we have here on the left-hand side, we're going to do this today. You can do pretty much the exact same thing. If you take minus the integral of E dotted into dl, then you get the voltage from the electric field. Or if you take the derivative of the potential with respect to the position, then that's where you get the electric field. So these things are all interrelated to one another based off of this more simplified than what we've talked about so far. Yes, it does. Does the voltage have relation to the original charge? Recall that we said that the force, let's just talk about point charges, for example, right? We said that this force here, if I could write it out to the side, is equal to KQQ over R squared, right? We said that this right here is KQ over R squared. It turns out that the voltage, we did talk about this on Tuesday, but we talked about a lot of things. This is equal to KQ over R for point charges. And this one right here is KQQ over R. So just a difference in a factor of R as you go up or down the vertical on here, and just a factor of Q as you go left to right. But that's how each one of these are related to one another. Okay? And someone might come along and say, okay, well, what about electric flux instead? We also talked about electric flux. And I'd say, you're exactly right. We talked about electric flux. I wish I could zoom over a little bit. Maybe I can just zoom out. So if we take the electric field and we integrate that electric field instead of over some path like we do here, but now we integrate that over some area, we called that electric flux. Right? So instead of integrating over some path, how it changes over some path to get electric potential, now we're just integrating over an entire area. Meaning how much of that electric field comes out of a given area. Right? And it just so happens that if this is over a closed surface, then this is going to be proportional. Actually, let's do it this way. If this is over a closed surface, then what it's related to is the charge within that closed surface. That was Gauss's law. Right? Gauss's law says that over a closed surface, the flux coming out of that surface is related to how much charge is inside of it, with the exception of epsilon naught. And if there's symmetry, then we were able to use the fact of this, or the matter that there was symmetry over that closed surface to recalculate the electric field. So in a nutshell, the six major concepts that we talked about so far, this is how they relate to one another, most succinctly. Right? It's that charges, a single charge in the universe, we can map that there is an electric field that radiates outward away from that charge if it's positive, or radiates inward towards the charge if it's negative. We can also represent that, okay, there is an associated electric potential associated with that point charge that exists lonely in the universe. And then, all of a sudden, follow these red lines back to the left, we pop into existence a second charge into this universe. Well, that second charge, due to the electric field or due to the repulsion or attraction, is going to experience a force, and there's going to be a certain amount of energy stored in that system. What is the energy stored in that system? Well, we related that to gravity. If you had, say, this was Q right here, a bunch of, some collection of positive charge, and you had Q here, Q prime, and let's call it negative, well, it's going to experience a force, right? And if that force moves this object through some distance, dl, to this position right here, then there had to have been work done for that to have occurred. And work corresponds to a negative change in potential energy. The fact that I went from this state right here to allowing that to do work on my object, the electric force has less potential to do further work, therefore its potential energy is decreased. Or if instead I had grabbed this charge right here, this negative charge, and I instead started raising it up here, you can imagine that since the force is pulling downward, I am storing more and more electrical energy into this system. Right? So that's how forces and energy related to one another. And this works exactly like gravity, right? When you lift something above the surface of the earth, we're storing more and more gravitational potential energy into that system. And so this idea between gravity and electromagnetism actually works really well until you remember that, okay, you could have a Q prime that looks something like this, but instead it's going to experience a repulsive force, right? And so I get the exact opposite behavior with this charge right here. I can move it closer and closer and closer to the original positive charge Q. And as I do so, I'm storing more and more energy into that system. And when I release this charge Q prime, it's going to take off and move out this direction, losing potential energy as it does, converting that to kinetic energy. So the closer I bring these charges into proximity to one another, if they are like charges, the more energy I store in the system, potential energy, and the further away I move it, the less energy I have stored in the system. So I've been monologuing and lecturing for 15 minutes now about this. What questions do you have that I can help bring all of this together? Maggie? U is the potential energy. V is the electric potential, not potential energy. So this has units of joules, and this has units, go figure, of volts. So potential energy don't forget the energy part. And this is just potential. Not confusing at all. But be that as it may, that's what they're called. Any other questions? Ben? An ion engine does use an electric potential to accelerate charges out, so you have some sort of emitter, right? And then you direct those emissions of charge out the back, but what you're doing is a momentum transfer at that point, or you're using conservation of momentum to actually do the propulsion. So since you're emitting something out one direction, you get an equal and opposite force. The only problem with an ion engine is you're releasing individual ions at a time. So 10 to the minus 27-ish kilograms. And you're trying to accelerate something that has a mass of 10 to the 9 kilograms, 10 to the 6 kilograms. I don't know what the scale is for a rocket. So you get very, very tiny accelerations on the rocket. Will it ever have what? Max kinetic energy? Yes. When it gets infinitely far away, right? That's when the potential levels out. For a point charge, what you get is, this is R, and this is U. For a point charge, the electric potential energy looks something like this. At infinity, the slope goes to 0. Well, if the slope goes to 0, that means the potential energy can no longer change. And if it's not changing, then it's not able to move energy into kinetic energy unless weak force decay of the ion or something like that. But electromagnetically, once it gets to infinity, its kinetic energy will be constant. In the natural world, do you ever expect a charge to get to infinity? The sun is constantly giving off what we call cosmic rays, high energy protons, right? So those charges, by the time they get to Earth, compared to the distance of the sun, that 93 million miles, they're not at infinity, but they might as well be. The amount of kinetic energy gains that they're getting every meter that they travel is so minuscule at that point. You could almost consider them as constant potential energy, constant kinetic energy, until they collide with the Earth's magnetic field, right, and create the ionosphere and all that fun stuff. you could do the math. I mean, I don't know what it would be, but I have a feeling it levels off pretty quickly as you come off the sun, right? I mean, it's just, or any object, right? I mean, that 1 over r is really going to eat your lunch by the time you get more than 10 meters away, right? Do electric fields, are electric fields generated by neutral charges? No, the very simple reason is because Q is 0. So no electric fields coming from neutral charges. And because we require that if the charge is neutral, even if there was an electric field that existed somewhere in the universe, say that E is already in existence, you multiply by a neutral charge, they wouldn't experience a force in that field. Now, if it's a molecule, a neutral molecule, you could polarize it, and you might get a torque, but it's not going to accelerate it one direction or the other. Yeah. Ask that last part again. Yeah. So as I move this down, you think of it like almost like a spring, right? I mean, it's not mathematically the same, but conceptually it's the same. I'm compressing that more and more. I'm storing more and more energy to where if I release it from here, it is going to move away, but it's not going to have that sudden jerk like it does if it's down here. Someone else is going to have to do work to get it to move closer, some outside force outside of the electric force. So whether that be me coming down and pushing it, like the classic example that I have is, I don't know if you guys were ever kids and did this. We would always have competitions in my pool growing up to see who could get the beach ball down to the bottom of the pool, and sometimes it would take 4 of us to get it down there. I mean, something else, its natural state is to want to be buoyed up by the fluid. Something else has to reverse that trend. So the work, you have to consider the change. So as the particle moves from here to here, from this energy state to this energy state, right? Up here on the top right, then I would have to consider this was U initial, and this is U final, and work equals the negative change in potential energy. But bear in mind that this is just the work done by the electric field, right? So in this case, I'm losing potential energy, so I would get that that's U naught minus U final, because I've got to take that negative sign into account. So it's not final minus initial, it's initial minus final. So in this case, the electric force, the electric force does positive work. So this, the way that I have it drawn right here, must correspond to this case right here. So what would it look like? Well, it's doing positive work as it moves this negative charge closer in. What we get instead is if this is a positive charge, U is going to look like this as a function of R. That positive time positive, if I'm looking at this right here, gives me an inverse function that's above the axis. So now if I am going from a high radius into a lower radius, right, I'm decreasing R. Well, this is U naught, U final. In this case, the work done by the electric force is going to be negative, right? So it's weird to think about that the electric field is doing negative work because things want to do positive work. So that means if it's doing negative work, there has to be something coming in there to balance the energy of this system that's doing the work to work against the negative work being done by the electric field. Okay. Let's press on. If you have more questions about this, feel free to come talk to me about it. A point particle has charge 2 microcoulombs and is fixed at the origin. What is the electric potential for a meter from the origin? How much work must be done to bring a second particle that has a charge of 3 microcoulombs from infinity to a distance of 4 meters from the 2 microcoulomb charge? It's a lot of words. So we said that electric potential is equal to some value at R minus V reference. And for a point charge, we said that that was R equals infinity. And we said that goes to 0. Or V sub R is equal to K Q over R. So I've got 8.99 times 10 to the 9 Newton per coulomb squared, meter squared, times a charge of 2 times 10 to the minus 6 coulombs, all divided by a distance of 4. Excuse me, I have no idea where that came from. 4 meters. This comes out to be 4.49 times 10 to the 10 to the plus 3 volts, or that's 4.49 kilovolts. Good? So we were just using our definition for the electric potential due to a point charge here. How do we calculate the electric potential energy of another charge being brought in from infinity? Yes, we multiply by the charge. If you didn't remember that, remember we've got this positive charge. Let's call this Q. And then we've got another charge, Q prime, that we are bringing in from infinity. So coming way from out here out to infinity. And so if you want to know the change in potential energy, the change in potential energy is equal to minus the work that's done, or that's minus F dot dl. This is just what we've written up above here. Well, that ends up becoming the change in potential energy. Another way that we could write that is the change in potential energy is equal to Q prime times the change in, electric voltage. Man, I did it again. So we've got the change in electric potential. Well, you say we only have electric potential here. That's because I made a mistake. There we go. Change in electric potential. It started at 0. It gets to here. So we've got delta U is equal to Q prime times V, or that's plus 2 times 10 to the minus 6 times the voltage of 4.49 times 10 to the minus, or 10 to the plus 3. And this gives me 13.5 millijoules. And you say, well, the problem didn't ask for what's its change in potential energy. The problem asked for how much work must be done to bring a second particle in from infinity. Well, the work done by the electric field is equal to minus 13.5 millijoules. So how much work must something else do to make this happen since we are doing negative work? The work done by some outside force has to be equal to this 13.5 millijoules to bring this in from infinity. So I think that gets to the question you were asking. Kayla? Are we using Q prime or are we using Q? For the calculation of V, we used Q, and now we're multiplying by Q prime right here. So we're implicitly using both in part B. Right, the voltage here is based off of, I see what your question really is. Is that what your question really was about? Okay. Okay, so if it were a negative charge, which one? Which one was a negative charge? If the second one was a negative charge, so if we made Q prime negative, right? Well, then I would get a negative value right there, right? And I would get a negative value right there. So the change in potential energy would be negative now, right? So the work done by the electric field, it would have done positive work. And some outside force, in that case, well, you really wouldn't even need an outside force, right? The electric field itself would be supplying the necessary energy to make this work anyway. So if this was a negative charge, it might say how much work is done by the electric field to bring this charge in from infinity. The work done by, to make something speed up, we have to have positive work done. And if this is coming from a state of rest at infinity to a state of motion, there had to have been positive work done by something. In this case, when the second charge is negative, the positive work is done by the electric field. In the case where Q prime is positive, we had to have something else make this happen. Yep. All right. Number 29 is basically an iterative approach to what we just did for part A. I have that solution posted online, and it just comes down to the fact that because these things are in near proximity to one another, you just end up taking that the net electric potential is equal to the sum of all of the potentials, or that's equal to the sum of K Q sub I over R sub I, their distances from the place that you're measuring. So let's, I really want to do this chart, or this problem right here, because it brings back something from last semester, again, that I'm assuming that at least one or two of you might have brain dumped since then. Protons are released in a Van de Graaff generator. The protons initially are located where the electric potential has a value of 5 MeV, and they travel through a vacuum where the potential energy is 0. So their delta V is equal to minus 5 I said MeV, it's just megavolt, so minus 5 times 10 to the plus 6 volts. Find the final speed of the protons and find the electric field strength if the proton changed uniformly, if the potential changed uniformly over the distance of 2 meters, right? So part A, how do I calculate the final speed of these protons? Well, what other quantity that we can relate to electric potential, meaning electric potential? Yes? Yes, okay, so what we want to remember here is that the change in energy when there are only conservative forces involved is going to be equal to 0, right? And the total energy is equal to the change in kinetic energy plus the change in potential energy, or the change in kinetic energy is equal to a negative change in potential energy, right? And we know that the change in potential energy is equal to Q, the charge that is experiencing this change, times a change in voltage. But I'm not told the charge here. What's the charge? Yeah, it's just one elementary charge. Q is equal to E. So I get delta T is equal to minus delta U is equal to minus E times delta V, or that's equal to, well, let's leave it there for a second. But how does that, if I find the kinetic energy, how does that help me find the speed? Yeah. Okay, yeah, what I was getting at here is that, remember that T is equal to 1/2 mv squared, in case you forgot that. And so delta T is equal to T final minus T initial. And it says it starts from rest, or it doesn't say that. Oh, yeah, it does, released from rest. So that means there's no initial kinetic energy. So that means T final is equal to minus E delta V, or that's equal to 1/2 m V final squared equals minus E delta V, or V final is equal to, let's see here, the square root minus the square root of 2E delta V over the mass. And the mass of a proton is something times 10 to the minus 27 kilograms. Can't remember what the coefficient is. Not again. Thank you. I will be back with you momentarily. You said 1.6 what? Okay, 1.67 times 10 to the minus 27 kilograms. And anybody who is following along might state, wait a second, I'm taking the square root of a negative number. My calculator will either give me an error or tell me that's an imaginary number. But what are we forgetting if we say that? Delta V is negative, so we're going to have two negatives here. So I've got the square root of minus 2 times 1.602 times 10 to the minus 19 coulombs times minus 5 times 10 to the 6 volts, all divided by 1.67 times 10 to the minus 27, 27 kilograms. This comes out to be a speed of 3.09 times 10 to the 7 meters per second, which poses a wee bit of a problem for us. So the question is the change in potential always going to be negative? It doesn't have to be, right? If it's starting from rest and it's happening spontaneously, yes, you would expect that. But what happens instead, if you do the photoelectric effect experiment, right? You have photons that eject electrons off of a metal. But then you have another plate over here that's called the stopping potential. We want electrons to come to rest when they get to here. So what happens is, remember, electrons spontaneously want electric potential to increase. So what we do is we force the electric potential of those electrons to decrease. And we end up getting it to slow down. It would be akin to some of the problems that we did last semester, just like where we started right up here, but where something starts with an initial velocity. A block is at the bottom of a ramp and has an initial velocity of 5 meters per second, and I push it up the ramp. How high up the ramp does it go? And so things will work out where you don't get imaginary numbers, but not because the potential always has to decrease. Yep. I said that this speed might pose a bit of a problem. Does anybody know why? What? It's very fast, yes. In fact, it's almost too fast. Yeah, so this is actually 10% the speed of light, and most calculations, when you reach 25% the speed of light, is when you say you can no longer ignore relativistic effects. So it would actually turn out that what would happen here is the actual speed of this object, if we were to bring relativity into account, I haven't done the math, but I would expect it'd probably be like 3.01 times 10 to the 7 meters per second if we took relativity into account. But this is an intro physics class, so we will not be taking relativity into account. But in case you're interested in the topic, there you go. You would have to consider the Lorentz transformation here. The classical argument is, okay, what if instead that this had been accelerated instead of through 5 MeV, would it have been accelerated through 50 MeV? Now we're right at the speed of light. Well, what happens if it was through 55 MeV? Well, classically speaking, then we have a particle that's traveling faster than the speed of light. And that poses a bit of a problem. Just a bit. Just a bit. Breaks space-time causality and that kind of stuff. But it sure does make for great Ant-Man movies. Or mediocre Ant-Man movies. Depends on who you ask. I tend to be in the latter camp. Find the accelerating electric field strength if the potential changed uniformly over a distance of 2 meters. So what is the electric field if the potential changed uniformly over the distance of 2 meters? How in the world are you going to calculate that? Go back to your concept map that we started class with today. How do we calculate how much electric field? Yes, Maggie. Yes, yes. So remember that electric field strength is equal to dV over dr. But if V is a constantly changing amount, meaning that the electric field has to be constant, it's the same as taking delta V over delta R. So that would be minus 5 times 10 to the 6 volts over a distance of 2 meters. There's another giveaway right there. Is we said in the last class period that one of the ways we can measure electric field strength is volts per meter. And so we've got minus 5 over 2, so that's minus 2.5 times 10 to the 6 volts per meter, or minus 2.5 megavolts per meter. And really, there's a negative sign. I knew something here wasn't working out the way it needed to. So we've got plus 2.5 MeV, or megavolts per meter. Now, I went to great extent to have positive or negative 2.5. I didn't draw any direction up here whatsoever. So help me make sense, because electric field is supposed to be a vector. So if this is a vector, and we're just talking about one dimension here, what's the significance of positive 2.5 megavolts per meter versus negative 2.5 megavolts per meter? Grayson? Which direction? And so all of this was, the direction that I presupposed without ever writing it up there is the direction that the proton travels. So if it had been negative, that means that the electric field was pointed opposite the direction that the electron travels. Or if it's positive, it's pointed in the direction that the electron travels. Now, when you release a proton in an electric field, what direction does it want to go? Against the electric field or with the electric field? With it. Positive charges want to move with it. And so, again, I'm just telling you, when I'm solving problems, these are the kinds of things that are going through the back of my mind. This is why you want to be concept strong, because it gives you some sort of intuition on whether your answer is right in sign or in magnitude or anything along those. Because I knew I wanted the answer to be positive because I needed the electric field to be going in the same direction that the proton traveled. I do tend to put positive or negative. But remember, if you didn't take me for Phys 1, my exams are multiple choice, the conceptual questions are multiple choice, the numerical questions are multiple choice. Generally what happens is if the answer is positive 2.5, that would be 4 out of 4 points. If you put negative 2.5, that'd probably be 2 or 3 out of 4 points. So you're still getting much of the credit. I probably would do 3. Usually if it's just a sign difference, then you get 3 out of 4 points instead. So you're still good in that regard. You just don't get full credit, I know. Every point counts. Literally. Yes, Grayson. I don't know how each of y'all think through problems. The question was, when should I have known that this was positive? The way my brain works was I knew the negative was wrong, and it took me a second to figure out why. And it was because negative means that for a vector, it's flipped over in the opposite direction, but that's not how charges work. So it was more when I saw that negative, it was like, wait a second, that's not how electric fields work and how protons work in electric fields. So, I mean, yeah, if you want to upload all of that beforehand, that's great. I'm a little better at uploading all of that beforehand when I'm just solving problems myself, like when I'm writing my own solutions. When I'm teaching in front of you guys, it's not until someone points out that you used the wrong charge or something like that, that I catch some of these mistakes. I have my solutions open over on my other screen there, but usually I'm solving these fresh every time, because if I just follow my solution, then I go way too fast for everybody. And some of you say you go way too fast anyway. I could just throw up the solution on a PowerPoint slide instead. Like, here's the problem, here's the solution, and we could move on with our lives. Yeah, relativistic speeds of problem solving in physics at that point. At least as far as it's relativistic for your brain, I guess. Okay. I love this one. I wish I had more that I could ask you that were like this, but I stumbled across this icebreaker question one day. I was like, yes, this is a beautiful thing. If you had me for Phys 1, you saw this one last semester, but it's still funny. I do reuse a lot of icebreakers, and because I wrote these all at the same time, the day 7 icebreakers for Phys 1 are the same as day 7 icebreakers for Phys 2. I guess in the future I'll have to come up with more Phys 2. I hardly ever see Carefree in a physics class. I'm proud of you guys. You should be a past leader in physics. That's just one person. Yeah. There are 2 that are relaxed, though. The sound of my sultry voice or something like that. I don't know. Stress. This is where I expected, most of y'all to be in this region. Stressed to B's. Angry. I'm not surprised by that one, too. What does he say in Cars? I have an effect on people that they themselves can't describe. I know exactly what the feeling is that I give to people in a physics class. I just make them angry or stressed. Nobody's ever excited to be in a physics class until we talk about briefly relativity, and then we move on and drop it. Yeah. Bees. Surprise, I brought bees to class. Okay, just kidding. Calculating the electric field from electric potential. We already drew this on the concept map. And so we've already discussed it a little bit, but it's the same as forces from potential energy. We showed last time that dV is equal to minus E dot dl, which means that we get no change in V by moving perpendicular to E. That's what the dot product gives us, that when you move perpendicular there, there's no change. We can recalculate the equation above and state that dV is equal to E cosine theta dl, or that would be the electric field that is tangent to the direction that dl is. So in the same direction as dl. That's why your book writes it that way. It's tangent to the path of your curve. Or a tangential amount of electric field is equal to minus dV dl. And you say, okay, what direction again is tangent? It's the direction that dl is pointing. In whatever direction your change in your path is pointing, and anytime you're talking about a change in a path, you're always talking about the direction tangent to the curve of your path. So this would be how much or how strong the electric field is in the direction of where you're taking a step. So if an electric field is in the x direction, the change in voltage with respect to y would then be 0. Right? If you had an electric field in the x direction, but I want to know how the voltage changes in the y direction, I would expect 0 change because those two things are not parallel to one another. In fact, I think it's the next slide, we call these 0 changes or directions where it will change, where there will be no change. We call those equipotentials. That is these little black lines right here on this figure. And really, if you were to imagine that this was, I don't know, some sort of extra strength Tylenol right there, capsule, that little positive charge, that those equipotentials are not single lines going around the pill. Instead, it's an entire surface that goes over the pill. So this might be the 100-volt line right here, and the 90-volt line, and the 80-volt line, and the 70-volt line, and the 60-volt line. As you move further and further away, the potential is going to decrease. But they're not just lines around that object. It would be an entire surface that goes over top that pill, that extra strength Tylenol. Okay? Equipotentials, where you expect the potential to be the same. And we said last time, please note that the electric field represented by the red vectors here is always perpendicular to the equipotentials. And now we know why. Because we only get electric field strength in the direction where the voltage is changing. That's what E10 equals minus dV dL means. That we only get a change when we change potentials. Excuse me, we only get an electric field pointed in the direction where the electric potential changes. That would be a better way to state that. Okay? Imagine E changes only in the x direction. This is the example that I previously stated. dV is equal to minus E dot dL. Should be a vector sign over the top of that. Sorry. Is equal to minus E dot dx in the I hat direction. Or that's EX dx, meaning that the electric field in the x direction is just the negative change in the voltage in the direction of x. I think this is what we stated last class period. Or if it was in the R direction, then we expect that the electric field in the R direction is going to be the change in voltage in the R direction. So if we then calculate that the electric field has X, Y, and Z components to it, then what ends up happening is that E is going to be the X component times the X direction, Y component times Y direction, plus Z component times Z direction. Or that gives us that this is minus dV dx in the I hat direction, dV dy, in the J direction, dV dz, in the K direction. And those are all partial derivatives, which means we're only taking the derivative that has explicit terms of the differential change, so X, Y, and Z, and that little magical upside down triangle that we talked about last time, the nabla symbol, the gradient. Well, if you want to know what that nabla looks like, it's going to be all of the directions plus times derivatives in each of the three principal directions that we're working in. And if you take electromagnetic theory, you will only find that this is the simplest one. Because then we can take nabla and dot it into vectors. We call that a divergence. We can take nabla and curl it into vectors. We call that a curl. Or multiply it, do the cross product. We call that a curl. And then you get into the fact that, well, not all coordinate systems are Cartesian. You have cylindrical and spherical coordinates, and you get a bunch of extra terms in with how the vectors change in the angular directions. It gets very complicated very quickly. As far as you need to be concerned in this class, most of the problems that we're going to end up working with are just going to be problems where we're changing in one direction. Maggie? Nabla is measuring the direction of greatest change. Yeah, greatest change. Not just direction and magnitude of greatest change. So again, you imagine that, let's pull up, here. Instead of just talking about contour maps, right? Let's go to Montesano State Park just for a wee bit and go to terrain. Yeah, here you go. You've got your contour maps right here, right? So if I were to drop a marker right there, and I was to take the gradient, nabla, onto these contours, then what I expect is, actually what happens is it's going to point up in this direction, and it's going to give me the steepness of that slope, right? But we're taking the negative, and so what happens is we'd actually point down this direction, the greatest change in the negative direction, and we'd get the magnitude of that change. If I were to come to, say, this point right here, the gradient changes very sharply, right? If I measure the gradient here, the gradient, the positive gradient, would be going up this direction. If I measure the gradient here, it's going up this direction. If I measure the gradient here, it's going up this direction. But it's always pointing up that contour map until we use in electromagnetic theory the negative, in which case we're always pointing down. You could think of it as if I were to take a bucket of water or a flood storm here in Huntsville and pour all of that water onto this point, where do you expect that water to flow? Well, it's some of it that lands here is going to start flowing down this way. Some of it that lands here is going to flow down this way. That's what gradient gives us. The rate of change, the steepness of the slope, and in what direction that greatest change is happening. Mm-hmm. First time I've ever pulled up Google Maps in a class. Calculating V from continuous charge distributions. You remember when we got to this for calculating E for continuous charge distributions, we spent an entire class doing really complicated integrals, right? Where we had cosine substitutions and tangent substitutions and all that kind of stuff. Instead, what I'm going to say this time is, here's the general principle. For a continuous charge distribution, the voltage is going to be the integral of K dq over R. Or, if you know, instead of the continuous charge, if you know what the electric field is in that region, we can integrate over the electric field. Meaning that for each of the major geometries, like the disk and the infinite line and all that kind of stuff, right? What you end up getting is you could do that complicated integral, or you could take the electric field that we calculated and do an integral over that electric field. What I'm going to ask you guys, or tell you guys instead, is look at chapter 23.4, so you at least know where some of these results come from. And because we've already done complicated integrals and you kind of see what goes into those, instead, after taking a note that you should look in section 23.4, if we have a ring of charge, it turns out that if it has radius A and you are some distance z above or on the axis of symmetry, then the result that you get is that the electric potential as a function of the height z is going to be kq, where q is the net charge on the ring, kq over the square root of z squared plus a squared. We could have done the complicated integral. This is the result that we would have gotten. The electric potential over the axis or along the axis of symmetry above or below a ring of charge is going to be this 1 over the square root of something squared. Which, if you go back and look at your solution for the electric field over a ring, we got almost the exact same thing. There was just a z hat vector tucked in there because electric field is a vector. And we said on that big concept map that when we go from the top of the map to the bottom of the map, they're only changed by a factor of distance. Well, what we had before was z squared plus a squared raised to the power 3 halves. Well, we go from the power 1 half to the power 3 halves. We've increased by a factor of 2 halves over our denominator. Our denominator is function of distance. So, yea, verily, we have changed by 1 unit of distance, going from electric field to electric potential, just like we should have. For a surface, a circular disk, if you will, the electric potential is really fun. It's 2 pi k sigma, where sigma is the charge density. Now, instead of the total charge, 2 pi k sigma times z magnitude times the square root of 1 plus r squared over z squared minus 1. So notice, just like on the last one and this one, if the charge is positive, then the electric field, if the charge is positive, the electric potential above and below the disk is positive. Unlike the electric field where it flipped directions. The electric potential does not magically go to negative below this disk. It's positive on both sides. But again, we don't care about that they're both positive on both sides. We care about in what direction is that electric potential changing. Well, for a positive disk, the electric potential decreases as you move away. Therefore, you expect the electric field to point in the direction of those decreases. Maggie? Same thing, yes. Magnitude of z is the same, is absolute value of z. Yes, absolute value. Sorry, I used those two interchangeably. I know. But I'm not a calc teacher. I should be. I would not have the patience to teach limits. I'd just say, listen, here's the shortcut. Don't worry about why. Functionally, this is what you need. And here's how you do the integrals. And here's how you look them up in an integral table. So that's Calc 1 and Calc 2 in about 3 days of class right there. I would not be a good calculus teacher. And now that we've talked about how to do derivatives and how to do integrals, here's where you can use them. And all of a sudden your calculus class has turned into a physics class. Oh man, optimization. That's a math methods class. That's awesome. And then you have to add some computer science stuff. And that's where I wouldn't be a good computer science teacher, because it's like, here's how computer science works. That's one day. Here's how you use Python is the next day. No C++ or any of that kind of stuff. I understand that the fundamentals are very important, and I don't want to diminish that, but I don't want to teach the fundamentals. I want to get to where you actually use the stuff. Over an infinite plane of charge in the xy plane, well, you end up having to, you have to do like a binomial expansion again over that square root of, whatever divided by z squared. And it turns out that you get that the electric potential is 2 pi k sigma times absolute value z, magnitude z, just to make the math teachers angry. Physicists are not good at making friends, right? We're socially awkward and weird. You guys will appreciate this. You're scientists and engineers. I was at Harding, and I was talking to a lady in the community who knew one of the engineering professors, and she was like, he's kind of odd, isn't he? And I said, I don't know. In my world, he's very normal. engineers, scientists, the rest of the world just doesn't know what to do with us. They stick us in labs and say, here's money, please leave us alone. Help us make society better, something like that, and have fun doing it. You notice here, actually, I want you to notice this. How does this relate to what we said the electric field above or below an infinite sheet of charge is? What? Yes, the electric field above or below an infinite sheet of charge is constant. Well, if I take the derivative of z with respect to z, the derivative of z with respect to z is 1. Well, then you have to consider its absolute value, so you do get a plus or minus there. That's where the electric field changes direction as you get away from the plane, or as you go across the plane, but still. Good. For a thin spherical shell of radius r with charge q, you get constant potential inside of the sphere, and you get the electric potential of a point charge outside the sphere. Now here's a question. Why does the electric potential not drop to 0 inside of the shell? Why does it not go down slowly? Why does it not immediately drop to 0? Physically, what would that mean if it did go to 0, either slowly or quickly? If it goes down linearly from here to here, then that means you get a constant electric field inside of that would have to be pointing towards the center of the circle, right? You're right. I'm saying you're correct. If the electric potential, instead of was constant right here, if the electric potential went down like this, then that means you get an electric field inside of that sphere. But Gauss's law says I only get an electric field when I've enclosed some charge. Well, inside the sphere, I have enclosed 0 charge. Yes, Henry? Yes, so what this is saying, since the electric potential is constant inside the sphere, it means that there is no electric field inside the sphere, which is exactly what we said we should get with Gauss's law. Good. So the electric potential inside of the sphere is constant. Now, if it's a uniformly charged sphere, what you end up getting is, well, outside the sphere, the electric potential is that of a point charge. That's good. But it does eventually level off to 0. The derivative at this point goes to 0. Someone tell me why, at the origin of this charge, both mathematically and or physically, why the electric potential, the slope goes to 0 at that point. At the origin. The slope goes to 0. Yes, the origin would be the center of the circle. So physically, we'd expect 0 electric field, right? We've encompassed no charge if our sphere, our integrating sphere, has radius 0. And if I've encompassed no charge, then I expect no electric field. You could also think about it as all of the different electric field components from everywhere inside of there. They all cancel out down there at the origin. Mathematically, you look there at the origin when r goes to 0, then I would get kq over 2 big R times 3. You could imagine if you take the derivative of this right here, then you still get something that's a factor of 2 times little r. Well, that means that the slope goes to 0 there as well. Where r equals 0, the slope goes to 0. That's good. And if the slope goes to 0, then that means, since the electric field is the derivative of meaning the slope of the potential, that means the electric field is 0. So whether you argue it mathematically, argue it from electric potential, or argue it from Gauss's law, there's zero electric field inside, even though the electric potential is non-zero there inside of the sphere, in the dead center, that is. So you get the strongest electric fields right here, right as you're getting to the outside of the sphere. How do I reason that? How do I say that the electric field is strongest right at the edge, whether you're on the inside or outside of that edge? Well, again, it's where the slope is the strongest, where it's the steepest. Yes, where it's changing the fastest is where you get the strongest electric field. Over an infinite line of charge, you get that the electric potential is 2k lambda, where lambda is the linear charge density. It's down here in the bottom right of the figure, times the natural log of your reference divided by r. And note here that the reference is not infinitely far away. That would pose a little bit of a problem mathematically. If the reference were infinitely far away, the natural log of infinity, there's another way that physicists tend to drive mathematicians crazy. We call the natural log log, and we call the log that mathematicians call log, we call that log 10. Because in physics, you tend to have the natural log show up actually way more often than log 10, so the natural log is log. The natural log of infinity is infinite, so that wouldn't serve us well for a reference point. But when you take the log of our reference at r equals to r reference, big R equals r reference, well, the log of 1 is 0. So yes, at our reference point, the potential is still 0. That's good. Any questions? Yes? How do you choose a proper reference point? That's a great question. Either the problem will give it to you, or because you're going to be concerned about how it changes, right? It might be a problem of you release a positive charge near this infinite line of charge. What's its speed after it's moved a distance of 1 meter? It doesn't give you a reference in that problem, but you only care about how the potential changes. So choose whatever reference you want. Choose the starting point as the reference, because then the voltage there is 0. Or choose where it ends as the reference point, because there the potential would be 0. Yes, ma'am? Lambda is the linear charge density. How many coulombs have we stored per meter of charge? Good question. All right. I'll see you guys on Tuesday next week. Have a great weekend.